welcome to this special coverage of the Astro Monkeys broadcast. I'm your host Jeremiah, bringing you the inside look at one of the most ambitious student projects in Purdue history, a spacecraft design that's going to target Saturn's moon Titan. Let's go take a look. Okay, so this is Shalav. He is the mission director for the Titan mission, and he will discuss some of the partners and what is expected for this mission. Can you give us a quick sight of what partners you are trying to work with for this mission?
Absolutely. So this mission is a collaboration across major companies in the space industry. SpaceX will be providing us with its Falcon Heavy launch system, and the other stakeholders include ESA, Aerojet Rocketdyne for its upper stage engines, and Johns Hopkins APL for the lunar configuration. We also consulted Caltech scientists as they work with JPL, Honeywell for avionics and communication, and Northrop Grumman for their docking systems.
And what are the requirements from these partners that you are working with?
Well, NASA laid out strict constraints for us. The mission must stay under a $4.5 billion budget, survive Titan's minus 260 degrees Fahrenheit atmosphere, and delivers scientific payloads on a 6.08-year journey through deep space. ESA and planetary science teams require that the lander must be sterilized to COSPAR Category 4 BC standards, and that it can collect and transmit prebiotic surface data from Titan. Our propulsion and vehicle sizing also have to ensure that the total stack mass stays within Falcon Heavy's LEO capacity, which is why we went with an expendable system. That's it.
Okay, well thank you so much.
Thank you.
Hi, I am with Ethan, one of the engineers that helped design this mission. So let me ask, what are the risks that were involved in this mission, and how did you categorize them?
Yeah, for sure. We really categorized it down to 6 different risks for our mission. Those being charged particles, space debris, manufacturing defects, solar radiation, communication blackout, and finally thermal damage. And the way that we kind of categorized these was by two different aspects. So first, the chances of it happening from a scale of 1 to 100%. And then the second part was the severity of the damage to our mission. And so, for example, with space debris, right, say we go and hit some space junk. Before our mitigation tactics, we had about over an 80% chance of it happening is what we estimated. And if it were to occur, it would be catastrophic to our mission. After mitigation, however, we were able to take that down to 1 to 10% chance of happening. And if it were to occur, it would only be minor damages to our mission. So.
Okay, well thank you so much, I appreciate it.
Yeah.
How did your team generate your concepts for the mission?
So we began by reviewing past missions like Cassini-Huygens and Voyager into deep space. And one of our first steps was laying out the delta V profile for each phase. But after that, it became quickly clear that our initial delta V estimation was 34 kilometers per second, and it was just too high. So we had to refine our model using the patch conic approximations, which brought us to a total delta V of about 20.5 kilometers per second, which dictated our mission design.
Okay, and how did this affect your stage sizing?
So we used MATLAB codes to size the rockets, each stage, based on 3 inputs: the delta V, the ISP of the fuel, and the final mass, which is essentially the mass of the stages above it that act as the payload. This allowed us to optimize each phase for performance while keeping the overall launch mass to a reasonable value.
What about your choice of your engines and your propellants for each stage?
So each engine and propellant was designed to fulfill a specific role for the mission. We used RP1 and LOX for the first 2 stages, which were provided by Falcon Heavy's Merlin engines. For stage 3, we needed a high impulse fuel, so we chose liquid hydrogen and liquid oxygen for the Earth to Saturn transfer, and this would be used by Aerojet Rocketdyne's RL-10C engine. And for stage 4, we went with hypergolic propellants, specifically hydrazine, because it's ideal for long-term storage and reliable ignition. We selected the AJ10-118K engine for this stage, which is also provided by Aerojet Rocketdyne.
Okay, well thank you so much. Okay, Shalav, so what did the final design look like for this mission?
Good question, Jeremiah. So the final probe is inspired by Cassini-Huygens. It's roughly 5 meters in diameter and includes an integrated heat shield, a parachute system, and other scientific equipment to investigate Titan's surface. It's designed to fit within the Falcon Heavy's 5.2 meter payload fairing and survive Titan's extreme descent conditions. The probe operates autonomously due to expected communication delays.
And what did your team take away from this experience?
So I think we learned that even small modeling errors can snowball into major design problems. Our original delta V estimate was way off, and that forced us to backtrack on our design. Working as a team in person has made a huge difference. Being able to meet, sketch things out, and debate trade-offs face-to-face really sped up our process. We also learned how important it is to balance creativity with realism. It's easy to design an ambitious mission, but making it feasible for future contractors is a real challenge, especially for an undergraduate team like us.
Okay, well, thank you so much for your time. I appreciate it. And that wraps up our report today on the Titan mission. On behalf of everyone here on the team, I'd like to thank everyone for watching, and I'll see you guys all next time.